This activity 3 continuing on, write a formula to describe the number of permutations of n elements with k copies. So we had 24, and then we talked about the repeated number of copies as the denominator, the factorial of the ratio. So if we have n elements, then there are n factorial way to rearrange those n elements. If there are k copies of an element, just one by the way, it could be more, but right now we're just talking one, then we divide by k factorial. This is saying that those copies don't have to be delineated by like a subscript 1, a subscript 2, a subscript 3. They're all the same. They're all the novels. Suppose Sophie has 2 novels and 2 science books. So now we got 2 copies happening here. The order of each type of book doesn't matter. So write an organized list of all the different permutations of Sophie's books. So she has 24 different ways to arrange them, but every time it's a novel and a novel that are in like this order, and if they switch, we're not gonna like bother worrying about if the order of the novels or science books switched. So this NNSS, that could handle 2 different ways, 4 different ways actually, and we'll talk about why it's 4 in a little bit. S or NSNS is another way, just kind of move one of those science books over. And so systematically, I'm going to be moving our science and novel books into a different arrangement. However, these 2 science books, they're different science books, but they just count for the same group. So they are copies on our organized list, and there are 1, 2, 3, 4, 5, 6 total permutations. How many repeated elements are there now? There's 2 novels and 2 science books. So because we now have 2 repeated elements, that's going to change our formula slightly from what we just talked about up here in question 7. Question 8, what method did you use to make sure you listed all possibilities? I mean, I just started systematically. Novel goes first, novel goes second, science goes third, science goes fourth, and I just slowly moved the science books over into the middle of the group. We'll do the same thing in question 9. Suppose Sophie has 3 reference books and 2 science books. No novels in this question. The order of each type of book doesn't matter. So the 3 reference books, R1, R2, R3, are all R. Same thing with science. Write an organized list of all the different permutations of Sophie's books. Now keep in mind, this is how I made my list. I started by saying all of the R's and then all of the S's. Then I said, let's take those double S's and I'm going to systematically push the double S, science, into the order of the reference books until science is leading the charge. It's at the front. Then I did the same thing with reference, and then these other ones too. I split science up, so they had 1 space between them. Then they had 2 spaces between them. Then they shifted. So I'm trying to move the science books across, move the reference books the other way, and balance everything out. And so as I'm working my way through making the list, this is the total list that I come up with. 2, 4, 6, 8, 10 total books. And yep, that works. That lines up. We still have 2 copied elements, but there's 1 element that's copied 3 times, and there's another element that's copied twice. Let's use our answers from question 8 and 9 to complete the table. And what question do we have here? How did you determine the number of permutations when the order of repeated elements matters? What pattern do we notice in the table? The table is already fully complete. So in the 4 situations, this is 4 factorial, and this one is 5 factorial. So the number of permutations is still based upon the factorial process. But if there were 2 repeated elements, the first repeated element, there's 2 copies, so 2 factorial. The second repeated element, there's 2 copies, so 2 factorial. When you multiply these 2 together, or if you like, when you multiply 2 factorial times 2 factorial. Now, the last one, we got 6 because we counted them. But there is a way to connect this one. I'm going to use some highlight here. There's a way to connect 4 factorial, which is 24, and the 2 factorial to make 6. That's the goal. The goal is to notice a pattern and to come up with the formula. And so I hope you're seeing, or eventually seeing, I want to connect this cell with this cell to equal this cell. How does that happen? Let's look at how question 9 was used to make this one. So question 9 has 5 elements, 5 factorial. The first element is repeated 3 times, so 3 factorial. This is the part to pay attention to. The second element, science and science, it's repeated twice, so 2 factorial. This is the part to pay attention to. This 6 is 3 factorial. This 2 is 2 factorial, which, boring, but it still has to be acknowledged. It is a factorial. So now, how do you take 5 factorial and these 3 factorial, 2 factorial, and get 10? By the way, we know there's 10 because there they are. I listed all 10 of them. But what if it was a larger list? What if there were more elements? How can these 2 small sample spaces let us know the structure of a formula? Pay attention to the order of the factorials and how they're used. Okay, in question 4, compare the values you divided by each time in the formula for the one repeated element to the division pattern with the repeated element. You see, in question 4, there were 4 novels. So 24 divided by 4 factorial, that gave us 1 when you had all 4 of them being repeated. There are 24 total arrangements. In questions 8 and 9, there are multiple reference books and science books. So we're going to multiply their repeated elements, 3 factorial, 2 factorial, to actually acknowledge there are 12 different arrangements we're going to get rid of. We're going to sort out those piles and cross them all out. And so in one of the previous activities, we listed and we crossed out duplicates, like part of activity 2. This is that concept, but we're just not going to write out every single arrangement. Let's actually develop a formula then, huh? Green. This is the question. This is the green question. Write a formula. How do you take 4 factorial and 2 factorial, 2 factorial, and get 6? 4 factorial is 24. 2 factorial, 2 factorial is 4. So if I divide, we get 6. That pattern, it also happens in the bottom one. Write it out first, pause the video and write it out. Resume the video and see if you wrote the same thing. This is what you should have written. 120 is the total number of permutations. Divide that by 12. For the number of copies, groups that we're eliminating, and you get 10 different unique ways. Within them, there are 12 combos, but we're saying all 12 copies within one group count as 1, and we're gonna just only count when the groups are actually uniquely organized. So to write a formula, I guess what number would go on top of our formula? We have n elements, k copies of one element, and h copies of the other. There's n factorial total elements. And then we're going to divide by the copies. So there's k factorial copies and h factorial copies. And we're multiplying between them. This right here is the formula when you take away the subscript 1, 2, 3, 4, and you just count all of that as the same element. Explain your formula using the meaning of the variables. N total number of elements, like 4 total elements. 2 of them repeat, 3 of them repeat. That doesn't make 4. 5 total elements. And point being, the copies. You put the factorial of the copies on the bottom. This isn't part of the math. It's one of the questions I've seen before. In the word cabbage, how many different ways can you rearrange the letters in the word cabbage to form new words or strings? 1, 2, 3, 4, 5, 6, 7 total letters that can be used. But A is repeated and B is repeated. And there's twice, BB and AA. So therefore, 7 factorial needs to be divided by 2 factorial and 2 factorial. When you calculate this, calculator time, when you calculate that, we will have the total number of ways to rearrange the letters in the word cabbage. So I'm going to do menu 1, 5. That'll clear the screen. Then I'm going to go menu 5, 1. Ooh, I need to actually put some numbers in here. I'm going to go 7 menu 5, 1 divided by, I think I like this button, control divide. I'm going to put 2 factorial on the bottom, 5, 1 times 2 menu 5, 1 factorial on the bottom. There's 1,260 ways to uniquely rearrange the letters in the word cabbage, but we don't need to say that the 2 A's take up more than 1 space. Thanks for watching, commenting, liking, and subscribing. This has been page 867. Does page 868 continue the activity? Yes, it does. Question or activity 3 continues on the next page. We'll see you there.